मी काल फोन केला होता त्यांनी उचलला नाही. Hello, Roop.
Yeah.
Hi. Okay. You want to check out this thing that?
Okay, I'm here.
Check the question and answer. तेरे को आता है कि नहीं, दिखता है कि नहीं वो?
Sorry. हाँ.
नीचे Q&A दिखता है कि नहीं?
Q&A दिख रहा है तो चैट डिसेबल कर दे.
हाँ, चैट है ही नहीं.
है, मेरे इसमें दिख रहा है.
तेरे इसमें, but it's only for you and me. This thing will not have.
Oh, fine. So that's fine.
Because what will happen is you will not know where to look, whether to look in chat or whether to look in.
No, fair enough.
Q&A will come.
Q&A is come. Yeah, perfect. Great.
Okay. And,
so, who's the other chairperson?
Nobody.
Just you and me, no?
Yeah.
Perfect. So you do the intros, and I will
do that question like you did, huh?
Yeah, I'll do the question answer. So I'll open a PowerPoint on the side.
Yeah.
Okay. Sure.
Yes, sound good. Okay.
So let's wait for him.
Yeah.
So let me know when you want to start sharing your screen. I will stop sharing mine.
His screen he will share at the end because that time when he wants to do the question answer.
Okay. Okay. मग चालेल, मग ठीक आहे.
Yeah.
Hello.
Yeah.
खाली ठेवून दे गाडी, मला आता नाही येत येणार खाली, बाहेर लावतो. खाली लावता कारण गाडी चावी वॉचमन कडे. हो. अरे मानसी.
हाँ सर, बोला.
Anil Seth is saying he's trying to log on and he's getting a meeting message that the host has another meeting in progress. मी त्याला परत पाठवलं लिंक, त्याला असं का गेलं?
मी त्यांची जी इन्व्हाइट लिंक आहे ती तुम्हाला पाठवू का सर?
पाठव पटकन.
So Sudhir, you do the intro.
Yeah. He's joined.
Great.
He's gone into the. Now he'll join in. Yeah.
Yeah, we have him.
Yeah. He had to join in as a routine delegate. Anil, I'm sorry. I don't know what happened. Why you got that message. So, can you hear me?
Good morning. I can't hear anybody, but I can see you all.
We can hear you. We are able to hear you.
I can see you too. I heard you too.
I can't, Vikram, I'll talk later. I'm in that meeting. Anil, can you hear? No, he doesn't seem to hear.
So maybe the volume of his machine is lower.
Does he have a WhatsApp or a phone?
No, but he's on email. Raising.
Hello?
Yes.
Yes, we can hear you.
Now we have you.
Can you hear us?
Hello.
I don't think so. He is able to hear us.
He's on chat.
Yeah. So you take over.
Great.
Maybe the volume of your PC.
In that case,
Now.
Can you hear us?
No, the volume is fine.
Are you able to hear us? No.
Let's have a look.
Try. Mansi, tana parat
Test.
login log off करेल से मुकते volume use the.
Hold on. I got it.
Yeah, he.
Okay.
Yeah.
Can you hear us?
I can.
Hear?
That's all fine. Yeah. Can hear
You
you.
can hear now? Okay, great. Okay. Sorry about, I don't know why you got that message that the host is logged in somewhere.
That's all right.
Okay.
Yeah.
I also noticed that this lovely screen you've got here says it's Saturday. It's Monday, isn't it? It's Monday, the 20th of April.
Yeah, these people are.
Oh, well.
Nobody saw that. See, that is what is the problem with consciousness.
Exactly. That's attention. That's a different thing.
Yes.
Yeah.
Well, good morning, everybody, or good afternoon there.
Yes.
So.
Just a minute.
Yeah.
There you are.
Okay. So, good afternoon, everybody. Good morning, Anil. Let me introduce Dr. Anil Seth. He is a professor of cognitive and computational neuroscience at the University of Sussex. He's a founding co-director of the Sackler Center for Consciousness, the Canadian Institute for Advanced Research, but mainly he's done a wonderful TED talk, and that's where I heard him. And it was an unbelievable TED talk where he tells you how your brain is actually creating. I won't tell you what he's going to tell us all that, but that TED talk is just fantastic. And that's when I thought we must have him here. We have had enough of neurology, but I told him that neurologists now need to learn a little bit about neuroscience, and that's why he's going to try and do this talk. Anil, it's all over to you now. Thank you.
Great, thank you. So let me just, thank you very much for the invitation to start with. Let me see if I can share my screen.
Yes, we have it.
You have it. Okay, so if I now start the slideshow.
Are there any videos in your presentation?
Yes.
We'll have to do a little setting before. Something called as optimize screen share for video clip.
Oh, yeah. Where is that?
So you'll have to stop sharing.
Okay.
and then hit the button share screen once. And just before you hit the blue
Oh, yeah.
on the left hand side, you have
Optimize screen share for video clip. Got it. Yeah.
Yeah.
All right. Perfect. Thank you.
Yeah, you're welcome.
So let's go. Okay. Well, yeah, it's a great pleasure to be able to speak to you all today. I can probably gather from my name that I have an Indian background. My father was from Allahabad in UP. And so I tend to come to India when I can. Last time was just in January, but looks like it's not going to be for a while at the moment. I cannot see anybody, so there's always this this strange thing with remote.
Yes, it's strange. It's different the way from normal talk.
Yeah. So I'm just looking at my own slides, and so I hope let's see how it goes. Anyway, so indeed, what I'm going to talk to you today about, and I'll probably talk for about 40 minutes or so, and then be happy to take Q&A, is about the neuroscience of consciousness. Now, I've become very aware in my career that there's a big difference between neurosurgery, neurology, and neuroscience. And in fact, not often enough communication between the different specializations, or at least there could be more, I think. So if by the end of this talk I can help build a little bit of a bridge between neuroscience and neurology, that would be a great pleasure and a great success. And perhaps the way to do that is to remind ourselves of what is the most magical thing that that the brain can do for us. And for me, this has always been the mystery of consciousness. And consciousness really is one of the biggest mysteries that we faced in science and philosophy. Why is it? If you think about it, from a certain perspective, 2 out of the 3 biggest mysteries about our place in the universe have already been solved. The first is literally about our place in the universe. We are not at its center. We are somewhere towards the fringes, this pale blue dot in the abyss. Then the second great mystery is our relationship to the rest of life. And Darwin cleared this one up for us, that we humans do not stand above and unique from all other animals. We are just one branch or one twig of this beautifully rich evolutionary tree, so that much of the machinery of life is shared with even the simplest of our other creatures. And the remaining mystery is this mystery of consciousness, of our inner universe. And what do I mean by consciousness? Well, I don't want to get too hung up on definitions, because definitions in science always co-evolve with understanding. They don't necessarily come first. I mean, in one sense, we are all familiar with what consciousness is. It is what goes away when you fall into a dreamless sleep or go under general anesthesia, or indeed if you're in a coma. And it's what comes back when you come round, wake up the next day. Consciousness is any kind of subjective experience whatsoever. And although it's the most familiar aspect of our existence, it's also the most mysterious. How does the private, subjective, what it is likeness of conscious experience, how can that be explained in terms of things happening in brains and bodies? How can the redness of red, the warmth of a log fire, or the pang of jealousy emerge from the physical and biological processes within our brains and our bodies? So this is just a schematic of the as yet still unknown connectivity of the human brain. This was from one of our papers a while ago, looking at the large scale connectivity of the brain. Now, you'll sometimes hear that there is this uncrossable explanatory gap between conscious experience and the physical world. That there's just no way in which an explanation that is phrased in terms of physical or biological stuff could ever tell us why any of that has to do with, is identical to, or is associated with conscious experience whatsoever. I mean, this idea of the insufficiency of physical explanation for consciousness goes back in history and in philosophy and in religion as far as you want to go. I usually go back to Descartes, especially in the West. Descartes, of of course, in the 17th century, cleaved the universe into two kinds of substance. There was res extensa, the substance that tables and chairs and brains and bodies are made out of, physical stuff that has extension in space. And there's res cogitans, the stuff of mind, the stuff of thought, the stuff of soul, and the stuff of consciousness. And in dividing the universe this way, he gave rise to the mind-body problem, and the philosophy of dualism, and things have never been simple ever since. And this idea, again, that scientific, mechanistic, physical explanations are not up to the job, that's Descartes, plagued the early days of neuroscience and of psychology, to the extent that for most of the 20th century, studying consciousness was considered rather irreputable, illegitimate, and certainly a bad idea. When I started my studies in the early 90s, I was repeatedly told not to think too much about consciousness because that would be definitely a career dead end and I wouldn't get anywhere. Well, I've got a career. I'm not sure how far we've got in solving the problem, but there we go. This is perhaps the harshest judgment about the science of consciousness. This came from Stuart Sutherland. Stuart Sutherland was in fact the founding professor of psychology at my University of Sussex. And he wrote this, in no other place than the International Dictionary of Psychology in 1989, so just a year before I started my undergrad. And he said, consciousness is a fascinating but elusive phenomenon. It's impossible to specify what it is, what it does, or why it evolved. Nothing worth reading has been written on it. And that's quite a harsh judgment of the field. Now, this way of putting things is now most closely associated with David Chalmers, who's an Australian philosopher. And his categorization of the problems of consciousness into the easy problems and the hard problems has become very influential. And here's how Chalmers describes the hard problem of consciousness. He says, I won't read out the whole thing, I'll just read out the highlighted bit, which I can't because it's covered by something on the screen. I can, yeah. He says, it is widely agreed that experience arises from a physical basis, but we have no good explanation of why and how it so arises. Why should physical processing give rise to an inner life at all? It seems objectively unreasonable that it should, and yet it does. That is the hard problem of consciousness. Why should there be any conscious experience going on at all when all that there really is in the universe are just physical mechanisms of varying degrees of complexity? Chalmers contrasts this with what he calls the easy problem, or the easy problems, plural. And easy problems are just the conceptually easy problems of figuring out how brains do what they do, how the mechanisms in brains and bodies solve problems in the vicinity of consciousness, things like perception, cognition, attention, action, language even. All of these things can be thought of in terms of functions, in terms of mappings between inputs and outputs. And even though the explanations are in practice very, very difficult, as you all know, they are conceptually not problematic. We all understand that mechanisms can give rise to functions. And then the hard problem is why and how any of these function performing mechanisms in the brain should generate a conscious experience. Now, I think this way of putting things has retarded the study of consciousness in science quite significantly, because it wraps everything up into one single big scary mystery in search of one big scary and unattainable solution. And there is another approach which I've, with a little bit of tongue in cheek, called the real problem of consciousness. And this is the way I like to think of things, is that to accept that consciousness exists and to accept that it depends on the brain in various ways, which we'll talk about. And instead of trying to explain the existence of consciousness in the universe in the first place, let's just characterize the properties of being conscious and explain those properties as far as we can in terms of mechanisms in the brain and the body. Now, that sounds a bit vague and abstract, but let me give you a quick analogy how this approach has worked before. And the analogy, and it's not perfect, and I very much recognize this, but it's helpful, is the analogy with life. Now, it wasn't that long ago that biologists, scientists of the time, maybe 100, 150 years ago, thought that the property of being alive could never be explained by physical mechanisms, that there had to be some kind of special source, some élan vital, a spark of life that made the difference between the living and the non-living. There was a hard problem of life. Now, we no longer think this. And as biologists got on with the job of characterizing and explaining the properties of being alive, things like metabolism, homeostasis, reproduction, then this big scary mystery of what life is faded away. And we now, although we don't understand everything, even about how a single cell works, life is no longer this conceptual metaphysical problem. Life is magical, but there's nothing magic about life. Now, we can come back to the value of this analogy later if you like, but I find it motivating that at least we can try. So what are the different properties of consciousness that we should attempt to explain? And here I like to divide things very roughly into three. There's conscious level, which is how conscious you are. For instance, the difference between being in a dreamless sleep or a coma and being awake and alert and aware. Then there's conscious content. When you're conscious of something, the sight, sound, smell, thoughts, emotions, and beliefs that populate your conscious experience at any one time. And then perhaps the most interesting aspect of consciousness is that of conscious self, the experience of being you or of being me. This is probably the aspect of consciousness we cling to most tightly. So let's take a look at each in turn, and I'll start with conscious level. What are the fundamental brain mechanisms that underlie being conscious at all? And this is probably where we approach neurology the closest. In fact, this figure is taken from a neurologist colleague and friend of mine, Stephen Lorry's, from several years ago in Belgium. So we can think of conscious level as being on a scale from being totally unconscious to being completely aware. And this is illustrated on the y-axis here, conscious level. And importantly, conscious level, I think as many of you know, probably all of you know, is not the same thing as wakefulness, as physiological arousal, which is along the x-axis. Now, they often correlate. So generally, the more physiologically aroused you are on this scale, the more conscious you are too. But there are exceptions. When you are dreaming in REM sleep, you are conscious, but you are by definition asleep. And off the diagonal in the other direction, there are a number of, and this is the terrain of neurology, there are a number of pathological states such as absence epilepsy, sleepwalking, very prominently the vegetative state or unaware wakefulness syndrome, minimally conscious states, where wakefulness can be preserved, but consciousness awareness seems to be absent. And of course, this is a field where the practical value of understanding consciousness is very, very important, because we want to, well, as clinicians, you would like to be able to determine whether somebody is conscious or not as directly as possible without relying on behavioral proxies, which may be mediated by physiological arousal rather than the mechanisms of awareness. And we can come back to that maybe later, because I think it's fascinating and it's been very successful already. So what determines being conscious specifically as opposed to just being awake? Well, there's some simple options. Is it the number of neurons? Well, probably not. We have about, as you know, about 80 billion, but 3/4 of these neurons in the brain are in the cerebellum, and the cerebellum doesn't have very much to do with consciousness at all. Is it any particular region? Well, again, you'll know better than me, there are certain parts of the brain that if they're damaged, you will lose consciousness forever. Certain thalamic or subthalamic nuclei, of course, widespread damage to the cortex can all abolish consciousness forever. But certainly these specific regions like the thalamic nuclei are better thought of, at least in my view, as a sort of on-off switches rather than the places where consciousness is generated. And of course, if you turn the computer off at the wall, the fact that the computer turns off doesn't mean that the power socket is explaining how computers work. And is it some characteristic pattern of neural activity. Now, early ideas about consciousness in neuroscience suggested that consciousness had to do with the amount of synchrony in the brain. So neurons that fire together, you get enough synchrony, perhaps at something like 40 hertz, then you have consciousness. This idea has rather fallen from favor because, again, there are certain prominent counterexamples. You have too much synchrony in your brain, you're going to have an epileptic seizure and lose consciousness. So the story is not quite that simple. And to cut a long story very short, being conscious at all seems to depend in quite specific ways on how different parts of the brain speak to each other. And one way to test this is a way we've used also in our lab at Sussex, is a combination of transcranial magnetic stimulation, TMS, and EEG. And the idea is to inject a pulse of activity into the brain using TMS, and then to record the echo using EEG. So it's a bit like banging on the brain with a hammer, and as if it's a very complicated bell, and then listening for the echo. So Marcello Massimini, who's another colleague of mine in Italy, have pioneered this approach to measuring conscious level. And what they see in sleep is that this echo is very, very simple, while in awake states, aware states, in this case, we're looking at the canonical sleep versus wake contrast, is very complex, very different. If you look at these two videos and they're slowed down massively, on the left, on the asleep, you can see there is still a response to the TMS pulse, but it stays very localized to where the stimulation was. It goes away, it comes back, but it comes back in the same place. Whereas on the right, in the awake state, the aware state, the response to the pulse is much more complicated over space and over time, disappearing and reappearing in highly intricate patterns. Now, what's exciting about this is that the complexity of the response to the pulse can be quantified. You can put a number to it. And if you can start to measure something, this is an important step on the road to its scientific understanding. And the way they do this is pretty simple. You basically just take the, you think of the response to the pulse as a vector over time, and then you can think of it as a single image and compress that image using the same sorts of algorithms that people use to compress digital photos that they send when you send something by email from your camera. And so this number is called the perturbation complexity index. It's the index measure of the complexity of the response to perturbation, so PCI, perturbation complexity index. And what you can see here is that this number scales and differentiates quite nicely between different categories of brain injury patients. So people who've been behaviorally diagnosed in the vegetative state have a very low PCI, with one or two exceptions. And people in a minimally conscious state have a higher PCI than severe brain injury, locked in state, have PCIs that are quite similar to healthy subjects. And in healthy subjects under anesthesia are low again. So this seems to be a measure that is tracking conscious level in quite a useful way. And data that I haven't got here shows that longitudinally, as single patients progress through a clinical trajectory, their PCI measure tracks their progression in quite informative ways as well. And you can even think of this cutoff level at about 0.3 that serves as some sort of improvised threshold for the presence of consciousness. Now, at Sussex, with colleagues there, Michael Shartner and Adam Barrett, we've been adapting these methods so they can work without this TMS pulse. So this is basically just computing the spontaneous or the complexity of spontaneous brain activity using EEG. And again, the idea is we translate spontaneous signals into this matrix of ones and zeros. So we just make it binary, and that provides then we can see how compressible that matrix is, and we get a measure of complexity. And we see a similar picture. So we see lower complexity under general anesthesia compared to wakeful rest, mild sedation in the middle. If we're looking at other kinds of data, here's data from intracranial electrodes in pre-epileptic neurosurgical patients. And what we can see here is that this is a nice contrast. Each of the graphs on the right show data from 4 different brain lobes: frontal, parietal, temporal, occipital. The main point here is that waking rest again is higher than non-REM early sleep, where consciousness is mainly lacking, but that wakeful rest and REM sleep, where dreams are common, are basically the same. So this is kind of nice evidence that here we have a measure that's sensitive to consciousness specifically, rather than sleep or stages of sleep. So it's going along with the awareness rather than the awakeness. That's shown there. And finally, just for fun, a couple of years ago, we did this study in collaboration with Imperial College London, looking at this measure of brain complexity when people were taking psychedelic drugs, psilocybin, ketamine, low doses of ketamine, and LSD. And what we found was that this measure of complexity, which is effectively in our hands here, just the diversity, the randomness of brain activity, goes up under these when people are taking these psychedelics at psychoactive doses. And this was quite, this led to some quite entertaining headlines, because, of course, a lot of cultural traditions associate psychedelics with a higher state of consciousness, a higher level of consciousness. And so, our results got massively misinterpreted to show that, brain scans reveal how scientists have created a higher state of consciousness. Nothing of the sort. What we've shown is that this measure of brain activity, which is quite simple, it's just this measure of randomness or diversity, is sensitive to the very global changes in consciousness that you get in psychedelics. And also, it's still the only example that we know of where this measure goes in a different direction to the baseline of wakeful rest. So all the other examples, whether they are anesthesia, sleep, coma, they all involve the brain becoming more predictable. Here we have an example of the brain becoming less predictable over time and space. So why should this work? This is an important question to ask. Why should this actually, what is the theoretical merit of measures like this? Well, this is why I've been motivated to use these measures, because it all goes back to an idea about consciousness that I first came across about more than 20 years ago, from my old boss now, Gerald Edelman, and his colleague Giulio Tononi. And they made an observation about consciousness, which I think is very, very significant. It's very simple, it's very significant, which is that every experience that we have is both highly informative, that is, every experience rules out the simultaneous occurrence of a large number of alternative possible experiences. The experience of pure darkness even rules out the simultaneous occurrence of a vast number of alternative possible experiences that you could be having. So it's highly informative in the very technical sense of reduction of uncertainty. But every experience we have is also highly integrated. It's all of a piece. We experience every conscious experience we have as unified. We don't experience bits of every conscious scene separately. So every experience has this co-expression of being highly informative and highly integrated, which means that we should look for the underlying systems, the mechanisms that are specifically associated with consciousness should also have these properties. They should be, on the one hand, highly integrated, and on the other, highly informative. And if we think of a general system of interconnected elements, we can think of this as a middle ground. On one extreme, you have systems that are fully interconnected, they're highly integrated, but they carry very little information. They can only be in a very few number of states. On the other extreme, we have systems where lots of elements that are completely independent. Now, this can carry a lot of information, but there's no integration at all. So it's somewhere in the middle, in this woolly middle ground of systems that are both somewhat interconnected, but also not too interconnected, that we have the capacity for both integration and information. And that's a characteristic of both what consciousness is like then, and what sorts of mechanisms we should look for that underlie conscious level. And this insight already helps us make sense of stuff we already know. So we already know, for instance, that consciousness is more associated with the cortex than, as I mentioned a minute ago, with the cerebellum. And if you just look at some gross anatomical properties of these two different parts of the brain, one thing that becomes very clear is that the cortex on the top is very, very complex. There are lots of cortical subregions are interconnected with each other in generally reasonably sparse ways, but they are interconnected. Whereas in the cerebellum, what we tend to have are vast numbers of pretty well functionally isolated subcircuits. It's a very crystalline structure in the cerebellum. So from this perspective, the cerebellum would not be the sort of mechanism that one would expect to generate the kinds of dynamics that would be associated with consciousness. So we're beginning to understand why these sorts of measures work. And what the next step then is to develop quantitative measures that we can apply to brain data that quantify this co-expression of integration information. Here, I'm not going to go into the maths at all, but I just wanted to give you a suggestion that we can go beyond now these practical measures that I showed data from that just look at how random or diverse or entropic the brain activity is, to measures that more directly go after this co-expression of integration and differentiation. And that these are promising ways in which we can develop a first or second generation of what you might want to call consciousness meters in the brain. And those, of course, could be extremely useful in all sorts of clinical contexts. I just wanted to, before I move on to the next section, just highlight this paper which came out earlier this year with a couple of colleagues in Trends in Neurosciences. And we just wondered about the possibility of islands of awareness, because from the perspective I've been talking about, consciousness becomes a property that's in principle expressible without any interaction with the surrounding environment. And of course, there are lots of arguments we can have about what extent the body and the environment is necessary. Well, it certainly seems to be necessary over time, but for consciousness in the here and now, maybe a brain in the right state is enough. And philosophers have long argued about brains in vats and all sorts of things, but it struck us there are some interesting situations now where we might consider the possibility of islands of consciousness in practice. And in particular, I wanted to mention to this audience something that we've been working on a little bit more now, which are hemispherotomies. Hemispherotomies are on the right, hemispherectomies on the left. These are operations performed usually in pediatric cases for severe epilepsy. And a hemispherotomy involves full disconnection of a diseased hemisphere, usually the right hemisphere, full disconnection of all neural pathways, but intact metabolism. So here we have a large piece of brain that remains alive, but is not connected to any other part of the brain or to sensory input or to motor output. How would we know whether such an isolated island of cortex is generating any conscious experience at all? We certainly can't make any inferences through behavior because it's disconnected. We can't deliver any sensory input either. So if we're even to think about answering questions like this, we need measures like the ones I've been describing that measure conscious level directly from brain activity. Okay, so that's the first part and is the longest part, I can assure you. And here's the idea that conscious level both went in terms of phenomenology, in terms of what we experience, and in terms of the mechanisms that underlie it, exhibit this complex balance of differentiation and integration. And if we can quantify that in precise and pragmatic ways, then we have the beginnings of consciousness meters. And also, and I've seen a couple of questions pop up, we can start to ask questions about how this balance is disturbed in a variety of neurological, but perhaps also psychiatric and neuropsychiatric conditions. Okay, so the next thing I want to ask is talk about is conscious content. So when you are conscious of something. And there is this conscious scene before you when you wake up in the morning and open your eyes. So what in the brain determines what we're conscious of when we are conscious? And there's a sort of a kind of straw man way to put this, which I want to get rid of or challenge from the start, which is that what we experience consciously is our conscious experience is some sort of direct window onto an objective reality that's out there, that what we see as it's just a window onto really what's there. And we know that this is a misleading and an inaccurate way to think of things from the very beginning. And I like to think of this in terms of our experience of color to start with. Color is something that's very well understood both from physics and from neurophysiology. We know that our brains, our eyes are only sensitive to 2 or 3 wavelengths, typically 3 wavelengths in the whole electromagnetic spectrum. Yet out of those 3 wavelengths, we generate an entire universe of color. Redness is not out there in the world or here in the brain, as a lot of artists have said. I think Monet said that color is where the brain and the universe meet. Our experience of color is constructed from wavelengths. So what we perceive is both more than, because we generate color, and less than, because we're only sensitive to a subset of the electromagnetic spectrum of what's out there. So what does determine what we perceive given the raw materials of sensory input? And the approach I want to take here is that your brain is a prediction machine. And that what you see and what you hear and what you feel are nothing more than your brain's best guesses of the causes of its sensory inputs. And I'll go into this in a little bit more detail. This is what I was talking about in the TED Talk, really. And so imagine being a brain. Just imagine that you are a brain. There you are. You're stuck inside a bony skull trying to figure out what's out there in the world. There's no light in the skull. There's no sound either. All you've got to go on as a brain is streams of electrical signals that are only indirectly related to things in the world, whatever they may be. These signals don't come with labels. They don't come with labels like I'm from a coffee cup or I'm from a table. They don't even come with being labeled as coming from the eyes or the ears or the heart. Perception, this figuring out of what's there, the causes of sensory input, therefore has to be a process of informed guesswork or of inference, in which these ambiguous sensory signals are combined with the brain's expectations or beliefs about the way the world is to form the brain's best guess of the causes of these signals. So the brain doesn't hear sound or see light. What we perceive is the brain's best guess of what's out there. And let me give you a couple of illustrations of this to show how this works. I mean, you've probably seen this before. You'll certainly have seen it before if you've seen the TED Talk, but these are sort of visual illusions which are quite common and quite popular. But I like to think about it in a different way. This particular one is called Adelson's checkerboard. And if you look at this, you'll see these 2 patches, A and B, they appear to be different shades of gray. I hope that works for you, however you're watching this. They certainly appear different to me. Yeah, but they are in fact exactly the same shade of gray. And I can illustrate this if I put it up here and I just join the 2 patches A and B with gray bars. And these gray bars are of a uniform shade of gray. And you can see it's the same shade. There's no transitions. There's no trickery going on. If you still think I'm tricking you, well, I'll just move this bar across and you can see it really is the same shade of gray. Take it away and they look different again. So what's going on here is that your brain is using prior knowledge built deep into the circuits of the visual cortex about how shadows change luminance of surface. So the brain, in some sense, knows that objects under shadow become darker, and that's why we see B as lighter than it really is. And of course, you're not consciously aware that your brain is applying this prior knowledge. So it seems real to you that B is lighter than A because you can't see the mediation of this perceptual process through the brain. Helmholtz, who sort of started really formalizing this idea of perception of inference, called it a theory of unconscious inference to emphasize that we're not aware of the process by which we perceive things, we're only aware of the results. Here's another example. This is a so-called two-tone or Mooney image. Again, you've probably seen things like this before. Now, if you haven't seen this specific example, what you probably just see is a jumble of black and white patches. But then if I fill the image in, you can see there's actually something going on here. There's a horse, there's a woman. The woman is wearing a hat and is kissing the horse. No, it's a rich scene. If you look at it for a little while, I won't leave it up for too long, but if I take it away again, now you can probably, hopefully, still see echoes of the horse and the woman in that image. If I leave it up for longer, it's more effective. But what's remarkable in this case and in a bunch of other cases is that the sensory information coming into your brain hasn't changed at all. All that's changed is your brain's best guess of the causes of that information, and that changes what you consciously see. So putting things this way dramatically changes how we think the brain does perception. And again, there's a sort of classical straw man argument here, which is that perception comes from the bottom up. This is a natural way to think about perception, that there's a world out there. There is a world out there. I'm not denying that we detect it through our senses, and sensory information just percolates deeper and deeper into the brain, and more at each stage, more complex information is extracted out. So things like lines and orientations at early levels, to objects, faces, more complex things at higher levels. And of course, in neurology, we sort of can understand all sorts of visual aganosias and visual disturbances this way. But in this view, perception comes largely from the outside in, or the bottom up. And this maps onto how things seem, right? It seems as if we're reading out the world and it's coming into us from the outside. But the prediction machine view is very different. It suggests that instead of perception depending mainly on sensory signals coming into the brain from the outside, it depends just as much, if not more, on perceptual predictions flowing in the other direction, from the top down or the inside out. And this is kind of a dramatic inversion. It may not seem like it to us that our perceptions are coming from the inside out, but this is what the prediction machine view suggests is really going on. There's a couple of ways to think about this. One is that this is the brain doing Bayesian inference. So Bayesian inference is a general framework for thinking about how to reason with probabilities, with reason under uncertainty. And we can think of the process of perception as the brain performing Bayesian inference on the causes of its sensory signal. So it's integrating prior beliefs, which is the Bayesian priors, with sensory data, which in Bayesian terms is the likelihood, to form perceptual content, which in Bayesian terms is the posterior. And how does it do this? Well, this is where these emerging, well, not emerging anymore, but quite popular ideas of predictive coding or predictive processing in the cortex come in. And so according to these views, this is a complicated figure. I won't go into it, but the basic idea is that these red arrows, which we can think of as sensory signals coming into the brain from the outside, they, instead of telling the brain what's out there in a direct sense, they just report prediction errors. They report the difference between what the brain expects and what it gets at every level of description, at every level of, let's say, the visual cortical hierarchy. The blue arrows are the perceptual predictions. They're the brain's best guesses about the causes of sensory signals or about the causes of inputs from the hierarchical layer immediately below. And predictive processing suggests that what the brain is doing when it's doing anything really, but certainly when it's doing perception, is trying to minimize prediction errors, trying to get these prediction errors down to zero, so the brain's predictions are very, very good predictions of that it's able to anticipate its own sensory flow very well. And it turns out that this method of minimizing of prediction errors can be shown to be a very, very good way of approximating Bayesian inference. So a brain that's doing this prediction error minimization is a brain that is performing approximate Bayesian inference on the causes of its sensory signals. It's a brain that's integrating its prior expectations with what's coming out there. And it's also a brain where perception is happening mainly in this top-down direction, with the bottom-up input just calibrating, keeping the brain's best guesses tied to their causes in the world in an appropriate way. I'll just give you a couple of examples, and I'm going to skip this because it's boring data. But one consequence of thinking this way is that if the balance between perceptual predictions and prediction errors goes a little bit strange, then that will have an effect on our perceptions of the world. And so we might see things that aren't there, or rather we might see things that other people don't report seeing. We might have an explanation of hallucination and delusion here. And we've begun to actually develop some computational models of this going on using deep neural networks. These are the sorts of very common now neural networks that are able to classify images very well. And they do it in a sort of bottom-up direction. You give an image and it feeds through various layers, and the output tells you what's there. But you can also run these networks in reverse, if you like. And what this means is you say to the network, there's a dog, and you update the image until the network settles into a stable state. And it's as if you're projecting a prior expectation of dog into the image. And we did this. We took a panoramic video of Sussex campus in the days when we were allowed to go to campus. And then we processed every frame of the image through this, what we call hallucination machine method. So we're imposing a prediction of dog deep into the image. It's not just like photoshopping dogs onto a movie here. They're organically emerging out of every part of the image. And it's a panoramic video, and people would put a virtual reality headset on and experience this. And it is kind of not unlike certain sorts of visual hallucination, possibly more psychedelic than psychotic. But what we have here is a way of beginning to model unusual conscious experiences that gets to the level of mechanism and process in the brain. Now, to just wrap up this bit, if on this view, hallucination we can think of as a kind of uncontrolled perception, wherein our perceptual predictions become untied from their causes in the world. They come loose from their causes. And if that's the way of thinking about hallucination, well, then we can think of perception, normal perception in the here and now, as also a kind of hallucination, but a controlled hallucination in which the brain's predictions are continually reined in by sensory signals coming from the world. So that's conscious content, the brain's best guess of the causes of its sensory input. And there's, of course, much more we could talk about here. But I want to move on and finish with this idea of conscious self. Because this is, for me and for many of us, the sort of central aspect of consciousness, is the experience of being a person, the experience of being you. How do we explain this from this sort of perspective? Well, there's a how it seems view, and there's a how things are view. The how things seem view is that there's a world out there which we detect through our senses, and the self is the thing that does the perceiving. The self is the recipient of all this sensory information. Forgive me, coffee. And that we then form perceptions of this external world. So here the self is something, sitting inside the brain that is doing the perceiving. What I rather think is a better way to understand it is not that the self is doing the perceiving, but the self is a perception. It is another kind of convenient fiction generated by the brain. And if the self is a sort of perception, it means that it's not this immutable, eternal thing that we should take for granted. It's something that is in need of explanation. And we can start by noticing there are many, many different aspects to being a self, just as there are many aspects to being conscious in the first place. When we think about experience of self, we have experiences of being and having a particular object in the world that's our body. We experience perceiving the world from a particular first-person perspective. We experience being the cause of actions, volition, what we call free will, if you like. We experience being a continuous person over time with a set of memories and plans for the future, what we might call the narrative self. And then we experience being ourselves in a way through the minds of others. So I experience being me partly in the way I experience how other people might experience me, which is a particularly strange thing to be saying, given I'm talking to a couple of hundred people, none of whom I can see. And many experiments show, and neurologists and psychiatrists know very well, that these different aspects of self can come apart in various ways, which means that the basic experience of being a self is a fragile construction of the brain. And there's many ways to investigate this. I want to focus on the embodied self just for now. And this is a demonstration you've probably seen before about how easy it can be to trick the brain into changing its experience of what is and what is not the body. So this is called the rubber hand illusion for those of you who haven't seen this. What's happening here is that the experimenter, the guy in a green shirt, puts a fake hand in front of the subject, the stooge in the blue shirt, and this guy is looking at this fake hand, and his real hand is hidden from view on the other side of this cardboard partition. And then the experimenter will take 2 paintbrushes and will simultaneously stroke the real hand and the fake hand, and while the person focuses their attention on the fake hand. And what happens is this feeling of seeing touch and feeling touch on an object that looks like a hand and is roughly where a hand should be seems to be enough evidence for the brain to make its best guess that the real hand or the fake hand is in fact part of his body. And so if you do something like this, you can test how it works. Now, this kind of experiment has gone into sort of psychology folklore as showing how malleable our perception of the body is. And in fact, it is not as compelling as people often will make out. You always know that it's not your hand. And in fact, there are probably better examples from neurology of things like phantom limb syndrome, somatoparaphrenia, and so on, where people have very disordered experiences of body ownership that are much more compelling to them as individuals. But nonetheless, it does work for some people. We actually did an experiment last year where we tried to characterize individual differences in the rubber hand illusion across about 450 people in the lab. And what we found, one thing we found was that the degree to which you experience the rubber hand illusion is very strongly predicted by how hypnotizable you are on a standard scale of hypnotic suggestibility. Now, this is very, very interesting because it first means that a lot of experiments on a rubber hand illusion are confounded and unreliable because they have not measured or controlled for hypnotizability. But it also shows how powerful hypnotic suggestion can be, and even when it's implicit. So here, just giving somebody a fake hand and doing this experiment is a sort of hypnotic suggestion, can generate real phenomenology. And I think that's also kind of interesting for a lot of cases where, functional motor disorders and all sorts of things that might crop up in a neurological context. We might think about the relevance of hypnotic suggestibility. Anyhow, it's still true that we can use these methods to manipulate people's experiences of embodiment in different ways. You can even give people a semi-out-of-body experience by having 2 headsets with cameras on, and then you swap the feeds so one person sees themselves from another's point of view. Then they shake hands with each other, and you feel quite oddly that you are shaking hands with yourself from a different first-person perspective. And this is relevant to the sorts of things people report in so-called out-of-body experiences, where they will say, I've seen my body from the outside. Now, this does not mean that some immaterial essence of self or soul has left the brain and gone floating away. What it means is that the brain has reached an unusual conclusion about where its first-person perspective is located. I think I'm running out of time a bit, so I'm going to just move very quickly to the end here and say that the thing I'm particularly interested in my own research is not just the experience of the body as an object in the world from the outside, but the experience of the body from within. This thing we call interoception, the perception and regulation of internal bodily signals, because I think that's fundamental to our experiences of selfhood and especially of emotion and mood. And one way to think about this is that emotions, which are very important aspects of self, are also perceptions, but they are perceptions of changes of internal physiology, that the brain's best guesses about the causes of changes, of the causes of interoceptive signals. Just as my perception of a visual world is about the causes of visual signals, emotions and moods are perceptual predictions about the causes of signals coming from within the body. And this is sort of a different way of putting some very old ideas from William James and Carl Langer about emotion as being a perception of physiology, but we're just putting it into this framework of predictions and prediction errors. And indeed, I mean, this is just like, this is an oldish study from Finland. This is not a scan. This is just showing when we think about emotions, we tend to associate them with different parts of the body. And there may be some underlying truth to that in terms of now emotions being literally perceptions of changes in bodily condition reported through interoception. And thinking about things this way is helpful because it can help us explain why our experiences of emotions and body are different from experiences of the world. You know, if I look at this coffee cup in front of me, it seems to be an object. It is an object. It has a back and sides and so on. Because the predictions in vision are about finding out what's out there in the world that's different from me. Whereas when I think about experiences of the body, and especially of the body from within, I don't just perceive these as objects. I don't perceive my kidneys as having a space and a shape. I perceive instead things are good or bad, or I'm anxious or not anxious. And this is because perception of the body from within isn't about finding out what's there. It's about control and regulation. And so that's going to have a different kind of phenomenology. When I perceive the body, I want to perceive how well I'm doing at staying alive. And so that explains why emotions are the way they are, and they're different from things like visual experiences. So we're beginning to get at how this way of thinking can explain not why consciousness exists, but why particular kinds of conscious perception have the character that they do have. And I've written about this a lot more in this idea of being a beast machine. The basic idea here is that this experience of self that we have is very, very deeply rooted in our bodily reality, in our flesh and blood material nature, and which is something that a lot of contemporary philosophers don't think too much about. They think we're some sorts of computers. Well, I don't think so. I think we are above all beast machines, biological machines. It's our brain's regulation of our biology that is critical in the experience of self. And thinking this way, I think we can start to then understand that these mechanisms of prediction of perception began in evolution, begin for each of us in development through this role in regulating the body. So everything that we perceive, whether it's an emotion or the world outside, they're all deeply rooted in this biological drive to stay alive. So I like to say we experience this ourselves and the world with, through, and because of our living bodies. So let me wrap up now, and just this last two sections, we've seen that what we perceive is the brain's best guess of the causes of its sensory signals, and that this applies not only to the world outside, but to the self too. The self itself is another kind of controlled hallucination, another kind of perception, and that a lot of the perception of self has to do not with figuring out what's there, but to do with control and regulation. And so we perceive ourselves and the world around us because of our flesh and blood nature. So just to finish, instead of Descartes, who might have said, I think, therefore I am, I prefer to say, I predict myself, therefore I am. So I think that was my last slide. Yes, it was. And I just wanted to finish with a very blatant plug I've just about, actually, I'll be sending off the final draft of my book this week to the publishers. I have a book coming out. Because of coronavirus, I think it's going to be delayed until May next year, but it will be coming out hopefully in India with some publisher. I don't know if it's been organized yet. Being You, the story of your inner universe, is already available on Amazon, even though it's not finished yet. And there is the TED Talk, as was kindly mentioned at the beginning, which just a very sort of shorter version of what I've been talking about now. All sorts of other places, if you're interested in finding out more. There's a very long 3-hour interview with Sam Harris from a couple of years ago, and I did a TED interview as well last year. And with that, I want to just acknowledge and thank the people in my lab at Sussex who have been helping with a lot of the experimental work over the last 10 years. And thank you for your attention. And that's it.
Right.
Thank you.
Oh, thank you, Dr. Seth. So my
thank
name
you.
is Roop Gursahani, and Sudhir and I are partners in crime. I'm going to actually, I've taken questions from the audience, and I'm going to share the questions right away. But
Oh, great.
okay, so but the thing I wanted to check with you was long ago, I remember trying to, well, I read through Dennett's book, and uh, I I was planning to do it again sometime, but I think I'll wait for your book to come out now.
Oh,
Well, you should do both.
I had a question, Anil, for you, which I've scratched out now. I had written any book plans, and here you have.
Yeah.
Yeah. So
It
can you
takes
see
a
these
lot. It
questions?
takes a surprisingly long time to. This is a. I think I started the book in early 2016.
Yeah,
It's taken a long time, but it's there now.
great.
Right. So the first question was from my senior, Dr. Chandrasekhar Meshram. Any particular reason to choose the painting by Dali at the beginning?
That's an unusual question. I don't know. It's a bit of a. That's kind of a psychiatric. I think psychoanalytic question there. It to me that I mean I love actually. I found a lot of inspiration in art for as an exploration of perception. There's artists have long recognized the constructive nature of what we perceive, and whether it's impressionism, which tries to not just paint the results of perception, but they try to invert the perceptual process. Impressionism is all about painting the raw materials, painting the light. And then Cubism is a real deep understanding of how we construct perceptions of objects. So there's a huge, I think, wealth in art and art history for neuroscience perception. I love the Dali stuff, I think, because it just emphasizes that consciousness is its own thing. It's not just that we open our eyes and yes, the world is sort of piled into our brains and we experience it literally as it is. Dali, through surrealism, just emphasizes that our conscious experiences are incredibly rich, incredibly loosely related at times to what's out there in the world, and emphasizes that there's a there when it comes to consciousness, a huge richness. But I probably used it because I found it on the internet.
Okay. So the next one is actually two questions that can be grouped together. I'll take Dr. Udani's questions together. They are, when does a child's brain reach adult levels of consciousness, and is autism a disorder of integration? You could probably take the
okay, those two questions. Yes. Both very interesting. I'm so this idea about the development of consciousness is fascinating, right? It's and it's something that I don't think enough has been done on in terms of these sorts of quantitative measures. I'm actually working with a colleague from Yale, Nick Turk-Brown, at the moment, who's looking a lot at the development of perception. We can go back to Piaget and think about different stages of development. And of course, things like certain aspects of adult consciousness that we take for granted only appear at very certain stages of child development. So there are some dramatic things like the emergence of language and the emergence of mirror self-recognition, which something we don't even think about, but is something that only a few non-human animals can do. And humans can't do it until about 18 months. So there is this sort of trajectory. I don't think, however, what I think is slightly problematic is thinking of adult consciousness as sort of up here and child consciousness as reaching it, as sort of on this trajectory to get there. I think in many ways, child consciousness is perfectly adapted for the environment that children exist in, and it's not this trajectory towards the ideal of adults. But quite what conscious level looks like during development is really not clear. I think it's probably, there's been this whole trajectory that we used to associate consciousness with thinking, with language, with executive processing, and the more we move away from that and think more in terms of perception, experience of emotion and self, that's more likely to be there in place very early on. Now, is autism a disorder of integration? It's I think a lot of people characterize autism that way. There's ideas. There's not really been anything, to my knowledge, that people have looked at this measures of integration and differentiation, measures of complexity in autism. Most of the research I'm aware of in autism has been looking more at what are the common perceptual features of autism. For instance, just as you might, in some sense, you can think of it as the opposite of schizophrenia. So people will associate schizophrenia with overactive perceptual priors. So you see things that are not there because you're projecting your expectations into the environment. In autism, there seems to be almost this opposite situation where there's sensory overload, where everything is clamoring for attention in your sensory environment. And so there is less sort of filtering down through perceptual priors. And there's some evidence for this, that you see sensory hypersensitivity in autism and so on. Whether that's a general explanation of autism is unlikely and unclear. And again, there's often this issue of lumping complicated spectrum disorders like autism together as if it's one psychopathology, when it's almost certainly not.
You wanted to ask something?
This about child reaching the level of consciousness. I want to know what about animals and even machines? But have you tried or thought of using your consciousness meter, whatever, as you say, on animals?
Well, that's a terrific question. And I think this points up a big problem with this consciousness meter approach, which isn't a unique problem to consciousness, but it's sort of been faced whenever in science you try and develop a way of measuring it, which is how do you validate it? So in humans, this sort of measures that we have, I think, are informative when they're applied to humans, or at least adult humans, because we have some benchmarks. We have a benchmark where we can be pretty sure somebody is conscious, and we can, in other cases, be pretty sure they aren't. And so we can then calibrate these measures against other reliable factors and then extrapolate and generalize. The further we get from these cases, these situations, the harder it is to generalize, unless we're really sure that what we're measuring is a sufficient condition for consciousness. And we're not at that stage yet. So I like to think of this sort of, how the development of understanding of heat happened in physics. A lot of controversy about developing reliable thermometers, because how do you do that until you know what heat is? And then people gradually became able to measure heat outside of the range of human experience. And then when we really understood what heat was as mean molecular kinetic energy, then we can measure the temperature of anything and it makes sense. But we haven't got to that stage with consciousness yet. So if I apply PCI to an octopus, I would not have any clue how to interpret the result at all. If I apply it to an orangutan, maybe there would be a potential to do so, but I wouldn't do it by comparing to a human level. I'd have to do it by comparing to an orangutan level, given, let's say, an anesthetized orangutan and a fully conscious one. So there is this slow extrapolation to the further we get from, if you like, the safe territory of humans. But it's very important to do so. And there's been this, when we think about the attribution of consciousness to non-human animals, certainly in the West, there's been a philosophical reluctance to do this because there's been an emphasis on language and on complex thinking. And of course, this traces to our human desire to see ourselves as superior to everything else. And if we have this sort of anthropocentrism, then we tend to deny consciousness to things that are insufficiently human. And against that, we have this anthropomorphic thing. So to the extent that things look human, we tend to assume they are like us. When, and this is for me super interesting. I've spent quite some time with monkeys, and it's very easy to become persuaded that they're little humans of some sort, little furry people, but they have no mirror self-recognition at all. They just can't do it. And there's some like, why not? What's going on there? So it's very easy to get it wrong on both sides, I think, when we extrapolate inferences about consciousness beyond the human, but we should do it. We should try to make some inferences.
Okay. So we'll move on. Sudhir.
One second. Those three levels of consciousness that you had, the level of consciousness, the content, and the self, can you apply that to animals? I mean, obviously the level we can make out that they are unconscious or they are conscious or aware or not. Then about the content you will not know, and about whether he has self feeling you will not know.
Yeah,
but
that's an impossible question.
Yeah, I think the value of thinking about other animals, what you might call the comparative study of consciousness here, is useful in two ways. Because we would like to know, and we have a better understanding of consciousness as a natural phenomenon by looking at how it might be expressed in other animals. It also makes us take our own human consciousness less for granted. Because, for instance, this idea of what it is to be a self. I mean, you'll know as neurologists, and one of my early experiences was reading the books of Oliver Sacks and people like that, which would just show you that after neurological damage, this thing that we call the self is changed in remarkable ways, and in ways where some aspects can be preserved and other aspects are gone completely or altered completely.
Yeah, so that's where we actually go on to the next question, and that's exactly the same thing. The vegetative state. Sudhir has already asked, I mean, how much brain can be removed, which parts can be removed. I mean, from me as a working neurologist, I was struck by Adrian Owen's, the stuff out there, which suggests that about 10% of patients who we think are vegetative state patients are actually awake inside.
Yeah.
So one is, I mean, if you could take both these questions together.
Okay, so yeah, I mean,
this is also asking you which part of the brain is really important for consciousness.
Yeah, exactly. And so I think I mentioned this a little bit at the early stages of the talk, that it depends very much which part of the brain you take out, and we know that you can have subthalamic strokes, thalamic strokes, which will abolish consciousness completely. What's sort of unusual here is that a lot of neuroscientists tend to associate frontal regions very strongly with consciousness. But it seems like you can have quite a lot of damage to frontal cortex without losing consciousness, without consciousness being very much disturbed. You take out more posterior regions, you have specific deficits in perceptual consciousness of one sort or another. But it's definitely an open question how much of the cortex you can remove before consciousness in total goes away. And certainly, the cases, to move on to the other question, cases of vegetative state, minimally conscious state coma, show that if you have a lot of diffuse cortical damage, that can definitely lead to the absence of consciousness, but still the preservation of wakefulness.
Any difference between the right and the left brain? Any difference between the right and left brain? Which part is more important for consciousness?
I'm not sure there is that much good evidence for that. And of course, there's still evidence that, for instance, we will know left brain damage tends to affect language. Right brain damage tends to affect more sort of holistic global processing of various sorts. But I don't think there's any evidence that says consciousness per se has a particular hemispheric asymmetry going on. And just to the question about, so Adrian, he's actually the co-director of this Canadian program with me that I work on. So I'm close colleagues with Adrian Owen, and his work is absolutely, it was very exciting. I didn't know him when it came out now 15 years ago. But it was incredibly influential then for precisely the reason that it was saying, look, we cannot just rely on external behavior to make an inference about residual awareness in these disorder of consciousness patients. And his experiment, which I didn't describe, which is this sort of classic experiment of simply asking people who were behaviorally diagnosed as vegetative, as lacking in consciousness, to imagine walking around the house or playing tennis while in a brain scanner. And then the idea was that if you saw brain responses consistent with understanding and following these instructions for mental imagery, that's very, very difficult to imagine happening in the absence of consciousness. And importantly, it wasn't just brain responses to sound, to or to their own name or something like that. It was, or to language. It was, imagine walking around your house. And so you have to engage in this mental imagery. We know in healthy controls, if people do that, you get activity in parahippocampal gyrus and all sorts of areas associated with navigation, which are different from the brain areas that are activated when you engage in imagery related to playing tennis or these fine, fluent motor movements. The problem with Adrian's approach, or the limitation of it, is that it might still be an underestimate, because in order for people to pass his test, they have to be not only conscious, but also linguistically competent, able to understand the instructions, able to have the mental competence and attention to engage in imagery for 30 seconds or more while in a scanner. You might miss them because a lot of these patients oscillate. They might have phases of awareness and you might just not have them in the scanner at the right time. So it's still, you might get a lot of false negatives. So the idea is to try and combine methods like this, which are very specific but lack sensitivity, with other measures that might be more like this PCI index that don't require the patient to do anything. You just bash their brain with TMS and listen to the response. They don't have to engage. So those measures have a greater sensitivity, but they might have less specificity. You might get some false positives. So you've got to combine these approaches. There's always going to be this trade-off between sensitivity and specificity, between false positives and false negatives. And at present, no single measure is going to deliver the goods. So it's about having a combination of measures that allow you to sort of surf that trade-off in the best way that you can.
Do you apply the TMS in various different spots?
The TMS, typically not. You tend to, that's a weird thing. It doesn't tend to not really matter where you do it from the point of view of the PCI. In practice, you'll avoid areas that activate loads of muscles. So you tend not to do it over the frontal cortex, because then you activate all the muscles that control facial expression. You get lots of contortions, and it's also quite painful.
Okay. So I'm going to, now there are some more questions here. Actually, there are a whole bunch of them, but I'm sure I really have to apologize to the others who asked questions, because Quick Gun Murugan gets it. So whoever sent off the questions while the talk was on, I could put them on.
Maybe we could mail you the questions later.
But let's finish off these that are there right now. We have about a few minutes to go.
Okay.
The first was about the default mode network, its role in consciousness, and default mode network activation exercises. I am not sure. I mean, maybe.
I mean, I will, given time, I don't want to say too much about it, because I haven't done much research on default mode network. I'm a little bit suspicious of it. So this whole idea of default mode network, right? There's this network of areas that we see correlated activity basically when a person is not doing an external task. And phenomenologically, it seems to be associated with the self. So people associate default mode network with sort of perception going inside. And you see often an anti-correlation between default mode networks and other networks that are more externally oriented. So whatever it is, it's something to do with internal, paying attention more internally. And so this is why then, to the second question, there's quite a lot of work that tries to associate default mode activity with things like meditation, with practices that bring the focus of attention more internally. Whether any of this, I think I'm very suspicious of accounts that use things like default mode to validate or to give validity to exercises of one sort or another. I mean, you can certainly justify meditation as being very good for you without appealing to the default mode network at all.
Autoscopy, the Oliver Sacks descriptions.
Yes,
some of it,
yes, I see that
bringing
one.
it up to date. Bringing it up to date. I mean, whatever Oliver Sacks described was a fairly long time ago. So, any.
Yeah, I mean, he was great. I was lucky enough to meet him a few times. He was very good friends with my my postdoc mentor, Gerald Edelman in San Diego, and Oliver Sacks used to visit now and again. I was massively influenced by him. I mean, it's all case study. That's the currency of a lot of neurology. And I know, and I'd be interested from hearing from you, but apparently he had quite a mixed reputation in neurology because he was sort of just cherry picking these cases and taking quite a lot of literary license with how he would describe them. That's what I heard, that his reputation within neurology was a little bit mixed.
Not a little bit. I have been massively influenced by him, by his book on migraine, and it's an. But anyway.
That's interesting. That's a great book because, of course, most people know his how the man who mistook his wife for a hat. But there's, I think his book on music is also brilliant. Musicophilia. Anyhow,
but he made neurology sexy. You can't deny that.
He definitely did. And there's a tradition of this kind of writing now, which I think has an allure. And the fact that you can personalize some of these stories, it just lends itself to the narrative form, and he was a brilliant writer. But there are limitations to the case study approach too. A case study is never going to give you a detailed systematic understanding of the mechanism across people. It gives you clues, but it's not the whole story. So I think that's where the Oliver Sacks it provides a lot of good starting points, and a lot of these neurological case series or case studies provide powerful examples that laboratory manipulations can only approximate. And we talked about that with the rubber hand illusion. And the same thing with angular gyrus and autoscopy, actually. So we have these virtual reality manipulations where you can put the headset on and you can think, oh, I'm seeing myself from the outside. But frankly, what you experience there is probably not even close to what someone having a very, very neurologically originated autoscopic experience is. And there's some very interesting work looking at seizure focus and sort of seizures that originate in areas like the angular gyrus, which seems to be implicated in registering different coordinate systems, the body-centered coordinate system with external frame of reference. If you have unusual and vestibular input too, if you have unusual stuff happening there, then the brain can come to a different conclusion about where you are. And there's Olaf Blanke, who's a Swiss neurologist. He's done some very nice work looking at stimulation of the angular gyrus. And this goes back to Wilder Penfield and these brain stimulation experiments, where, again, through direct brain stimulation, you can generate very powerful changes in conscious experience, things like autoscopic or out-of-body experiences. And that's very compelling evidence that these properties of self are constructed on the fly. If you can change them just by a gentle electrical tickle of a particular part of the brain, well, there's nothing that's pretty interesting.
Yes. So we have a whole bunch of questions. So if you don't mind, what we'll do is probably download them and send them across to you. And if you feel up to it, be good if you can answer them, and we'll send them out.
It would be a pleasure. I will definitely try to do that. I'm
Sure,
sorry I went on for a bit longer in my main talk than I was intending.
No, we could go on. We could, but I mean, really grateful to you. I mean, you've given so much time. And it's important for us as clinical neurologists to understand what neuroscience is really up to. Because, lost in, the nuts and bolts of it, understanding the wider picture, at one level, we are technologists. We need to know the science.
What is it about?
Oh, I mean, I'm super grateful for this opportunity. I'd love to hear more, more about what you're all doing in India, and I think it's terrific that you're organizing these webinars at the moment. I think it's a fantastic initiative, and
we're really grateful that you wrote back immediately and accepted our invitation. And I mean, like I said that night, I could not believe it when you wrote back. Very happy.
Well, as you said, we're all kind of stuck at home at the moment, so it's the time to do it, isn't it?
Yes.
And so thank you for the invitation, and by all means send along the the questions, and and people this Twitter, you can follow me on Twitter and on the website. By the way, my website, if people are interested in the book, it's still a year away, but you can sign up for updates about the book progress.
The book is available on.
It's not available. You can pre-order it, but it's not available yet. It got delayed because of Corona, of course, and so now the scheduled publication is for May 2021.
Okay, so if you want any proofreaders, you have lots of them.
Thank you very much.
Right.
Okay.
Have a good day. Thank you.
Bye.
Have a good afternoon. Thanks again, and we'll be in touch.
Bye. Bye.
Bye-bye.
Oh.